now I'm recording. Zoomers, we're still good? I got you. Excellent. So the goal of lecture 1 is to gently ease us back into what you should already know. And if you've never heard it before, it might sound faster. But I wanted to start with stuff you know to emphasize the software part, because I believe that the software will be new. And so I believe very strongly in not trying to do too many new things at the same time. So this unit is familiar concepts, where the new part is the implementation in Stata and R. All right. And in this unit, I did separate videos instead of a handout to show these things. So a lot of the syntax and output is within the slide deck this time. The videos are posted for homework 1. That's where they're posted. So you can work through these files and run things on your own to learn how the software works. So first thing I want to talk about is just data sets, because this is a topic that doesn't really get taught very much. So just to give you a few tips on how to enter data if you're forced to do that, and then how to think about merging data together. So quantitative data can be stored in a variety of formats. You do not need to work with SAS or R or Stata directly when you're entering data. Things like Excel is just fine. It's totally fine. And actually, all of the data examples that I'm going to give you this semester and for your homework are going to be in Excel format. That way you can open them no matter what. You don't have to be inside the software package, and you can look at the data yourself before you do anything. So there's 3 steps to importing that kind of data. Save it to a folder and get the place that it is. Put the place that it is into the syntax. So that's the first thing that has to happen, is it has to know where your files are. So save it somewhere and get that address, and then run the syntax to import the data. And I'm going to give you examples of what all of this looks like. So historically, this has been the most difficult step, just getting used to the system, getting into the virtual desktop. So that's why I have all the videos to help you that you can work alongside to go for that. So for each column in a data set, most of our data sets are structured so that a row is a person and a column is a piece of information about that person called a variable. And a column, a variable, usually has 3 pieces to it: a name, a label, and then a value labeling convention. So when you are entering data from scratch, for instance, names have formats that all software packages make you obey. If you have spaces in your name, it will convert them to dots or underscores. If you have special characters, it might yell at you or it might try to convert them. So try to get in the habit of making names without spaces. I would use underscore if you want to create what looks like separate words. That way the program understands that. Dots are also okay in R, but not in other packages like SAS. And they have to start with a letter. Variable names cannot start with a number. All packages have this rule, and I don't know why it is. It used to be the case that variable names had to be 8 characters or fewer. That is not true anymore, but just keep in mind that the longer you make your name, the more typing you're going to have to do later. So you want it to be long enough that it's descriptive, but not so long that it becomes annoying, somewhere between the two. Now you know what your variable means, but someone else may come along and be like, what does this column mean? That's where the idea of a label comes in. And that is a longer string that is attached to that column that shows up in your output or shows up in the data set, where you can enter a longer description as to what it means. R doesn't really use it, but every other package does. And future you will greatly appreciate it if you add labels to everything you do. Longer text, so I think SAS is like 250 characters or something like that. It can be quite long. So these are examples of what you might talk about, how it was made, why it was made, what it's for. And then for data that are kinds, not really numbers, so categories, groups, that kind of thing, you would want to create a labeling convention in the software that says 1 means this, 2 means this, 3 means this. Because that way that shows up on your output. You don't have to remember what 1 means and what 2 means. And someone who's looking at your output will know that as well. That is something that is built into other packages that is not as easy in R, but I figured out a way to work around it to do that. So you will see in my programs all of these pieces of information to go with the columns that you have. So when you are entering data, it is fine to do it in Excel. Absolutely fine. But just keep in mind that formatting does not transfer. So for instance, If you like, all the cells that are yellow mean this, and all the cells that are red that mean this, R is like, yeah, I don't care. R is colorblind, so is Stata. All of that information has to be codified in a column. Like where it used to be yellow and red, make it a 1 and a 2, something like that. It has to be stored separately. It can't be a format. Put the names in the first row of the spreadsheet. Don't have like multiple sections with names because it will not import correctly. If you put the name that you want in the first row, there is always an option to say name the column this within the software package. Then you don't have to do any extra work to list them. Start with a letter, not a number, and I would use stems to make things easier to organize. So for instance, if I have a 10-item measure of stress, I might have people answer questions like, how anxious do you feel right now? How stressed do you feel right now? How sad do you feel right now? And I might be tempted to name those anxious, stressed, and sad, because that's what they mean. But honestly, a better strategy would be like stress 1, stress 2, stress 3, because all of the packages have ways of abbreviating lists like that. And you don't have to type out every single element if you name it in a way that is obviously sequential like this. And it's the suffix that becomes like this. So one well-being is not the right answer. Well-being 1 is what you want to do. It's the end that makes the series. For categorical variables, please don't type text. Do not enter text when you enter data, enter numbers, and tell people what the numbers mean. So the reason is that text, or string variables as they are sometimes called, are both case and space sensitive. So if you have an RA who types control group lowercase and another RA who types control group uppercase, that is not the same thing. And believe me, there is an infinite number of ways to misspell something or to mess up the capitalization, and you do not want to do that to yourselves. So get away from words if you can help it. Use numbers. Control group is 0, treatment group is 1, something like that. You can add variable value labels in your program to indicate what things mean. And when I do this, by the way, I always put the number that is represented along with the label that I want. So 0 dot control group, 1 dot alternative. Do you know why that is? If you don't, a lot of packages will reorder them alphabetically. So control would go after alternative, which is backwards from how it is in the original data. So to keep that from happening, I put the number in front. Keep my own sanity. Do not mix text and numbers in the same column. It will turn the whole thing into text. So if you have like a missing value or something that someone said that wasn't a number, don't put it in that column. Make a new column just for that. One other thing that you may have been taught that I'm going to teach you not to do anymore is missing data codes. Like -99, some people enter to explain that that is a missing value. You know what the default is for missing? Blank. Leave it that way. It's fine. Otherwise, you may end up with data that are read as real values when they're actually codes for missing, and that becomes a nightmare. So just leave it blank if it's missing. It'll be fine. In terms of building data sets with different structures, this is something that I've had to help people troubleshoot and spend a lot of time on that could be avoided. You don't have to have one data set for a project. I would get in the habit of using one data set per dimension of sampling that you have. So for instance, if I have a longitudinal study of children in schools, so I want to know one data set for occasion level information, one data set for school level information, one data set for kid level information. Keep them separate. That way you don't have to drag the same value down across all the rows that belong to the same person or the same unit. You can always merge them together on the back end. So hang on, there we go. So for example, I have a different example. People collected from different countries. I would have one database that has one row per person, and I would have an ID variable for which person it is. I would have a variable for which country they came from, and then all person level information. I would have a separate country level database where it's one row per country. I would have the country ID variable and then all that information. Otherwise, if I tried to put the country level information into the person level database, what I would have to do is for all the people from the same country, drag, enter all the numbers across that country, drag, and that's inefficient. So you don't want to have to do that. There are ways to merge these things together to get to the right dragging structure to code that information. Same thing if I have a longitudinal study. 1 row per occasion would be one data set, 1 row per person would be the other data set. So if you are ever faced with a data task that is manual and repetitive and you're like, there has to be a better way, stop and send me an email, okay? There probably is a better way. I can tell you some horror stories. I once had a student who, her and her son, she paid him allowance, spent the entire summer doing something to an Excel data set that I could do in 3 lines of code. Manually rearranging things because she did not have exposure to software. As a graduate student, I had exposure to software, and I once spent 6 weeks generating output and building it into another data set that was 3 lines of code that I learned about later on. So, especially for things like if you have different data sets for each subject and you have to put them all together into one thing, there are ways to have it iterate through and do things like that for you. So any any task that is like the same thing that's over and over, you just change one thing, there's a way to do it in code, I guarantee it. Okay? Just trust me on this. Do not spend your time manually manipulating data of any kind. There's always a better way to do it through syntax. Speaking of which, here's some tips for syntax. So I have an example that you don't have yet, but I wanted to show it to you. This is an example of what is going to be example 2 using R. So all of my syntax files have the same type of structure, and I would like you to get used to using a structure, not necessarily mine, but a system. So all of my files have the same kinds of options. I have generic options first for how I want the output to be displayed, how wide I want it to go, how many significant digits, that kind of thing. In R, this section here refers to packages. So R has a very limited series of built-in things. Others you have to add from an external environment. So at the top of all of my R programs that I'll give you, I will have code that looks like this. If require read Excel install package library. So what this means is, hey, have you downloaded this before? If not, it will go and do it for you. And if you have, it will download it and skip that step and then just load it. So every time you open R or any package, you have to reinvent it by hitting that and running it again. It doesn't have memory. Like when you shut it down, it doesn't know what you used to do. So in R, you have to load packages by having this library command. That essentially brings them into memory and allows you to work with them. Otherwise, the commands won't work. So I list all the packages that I want first. These things you will see in my program, these are just organizational pieces. I call them comment blocks, section headers. They're meant to make it so that when I'm scrolling really quickly, like I can figure out what section I'm in, because it's like this block does one thing, the next block does another thing. Note that this is R code. This is built out of what those of you who are young might call hashtags. Old people are going to call pound signs. 6 of one, half a dozen of the other. It's that symbol in R to make comments, and so like I make a box here that says begin data description, but before that one was data import and manipulation. So you tell it where your stuff is, setting a working directory. That way it knows to go to that place to look for any files that you refer to from that point on. Reading in the files, so I'm importing Excel data into an R format. I have labels here and comments because R doesn't use those. I have a way to save your text to a separate text file that you can use if you want to. And then you have all the stuff that you want to do. So describing variables, running models, and the end of it is then closing the output file. So you don't have to have the output files, but this kind of structure to where you have what are the things needed to do to the work, what's the data that's needed, what are all the changes I need to make to the data, and then what am I going to do? The other piece of it is, and I think, yeah, I have that, yeah, okay. I'm going to have you do the same kinds of things over and over again. So you might have one command that does like for one variable, and then the next question will be like, do it again for the other variable. Do not undo what you did and change the name. Instead, like take what you did before, make a new copy of it, and then change it there. So that cumulatively, you know every step that you did. Otherwise, you may have to end up retyping things that you already did. Plus, find and replace is your best friend. So when I give you these sorts of files, find and replace can get you pretty far in terms of changing the names of variables and data. I don't want you fighting with R if I can help it, or Stata for that matter. Also, in the bottom of Stata and R, there is a little window that looks like this where you can type things and have them activate like immediately. Don't do that because there's no record of it. So that work dies at the end of the session. You have no record of it. Whereas if you build these syntax files, then if you have to do the same thing on a different data set, you run it and it's done. That happens a lot. I can't tell you the number of times where I've went through a series of very complex analyses and then gotten an email that said, oh, I forgot there are 4 people that shouldn't have been in that file. Can you do it again? Now, if I was doing things manually one by one, I would not be happy. But if I have a script, I'd be like, oh, I could do it again, but that's going to take 3 weeks, sorry. And then they go away, and I'm like, click, and now I have 3 weeks because, I have a syntax file. So future you will appreciate your efforts to make syntax that is helpful and complete. It's also good for reproducibility. I can tell you that one of the reasons that some of my papers are more highly cited than others is because as a supplemental file, I provide syntax. I show them how to do things, not just report what happened. And people can use that as a template and they end up citing it as a result. So that's what I want for all of you. All right, a little bit about data and syntax. Again, I'm happy to be a resource. If you need to do something that is repetitive or otherwise you don't know how to do it, I can try to help you get in the right direction. So any thoughts or questions on that? Okay, we're all good? Okay, as a reminder, anyone who's shy can send me direct messages in the chat. I'm keeping an eye on that, or you can direct message Erica, who's sitting back there monitoring, right? Yep, okay. She's quiet, so I try to get her to talk. Like, no, I'm not. I know, I'm quiet too, totally. No, I'm not quiet here. Like if you meet me at like a cocktail party or a reception where we're supposed to be nerking, oh, I'm sorry, I didn't see you there. Yeah, you're not in my Zoom room, I don't think. So that's why. They can yell at you in person. Yeah, but no, like if I have to go to a reception and like network and make small talk, I am like the shyest, most awkward person ever. But you put me in front of a room full of people and I'm totally fine. So, who knows? All right, so about variables. Then, what kinds of information can you work with in terms of quantitative data? This unit is about just summarizing them individually, univariately. I want to give you a taxonomy in terms of how I think about variable types. It's related to levels of measurement, but this is more like how to model them as a perspective. The big picture, when you have a data set that you're doing analyses on, you have to ask yourself, is this variable categorical or quantitative? Is it kinds or is it numbers? That is the biggest distinction that matters. So this types taxonomy will guide 2 things: how you would go about summarizing it, describing its salient features, and how you would go about analyzing it in terms of including it in models. The kinds has more to do with when there are outcomes, but certainly for summarizing, that's going to matter. So the apparent purpose of this unit is to review univariate descriptive statistics. Univariate means one variable at a time, not how they relate to each other, just how much is it on average, that kind of thing. Descriptive is a word that means we're not testing anything, we're not making any claims, we're just presenting information. And statistic is a characteristic of a sample covering population. The actual purpose of this unit is to give you familiar material with which to approach unfamiliar software. Homework 1, your first real homework, is essentially going to teach you how to write a method section. How do you get the information out that you would put in a method section, and the results section for it is going to look like a method section. So, step 1. So categorical. There are 3 main distinctions here, but the big picture is that a categorical variable, the number is not a number, it's a label. Binary, first one. Binary means 0 or 1 specifically. Dichotomous is a synonym, but that means 2 kinds, but they can be any number. So, are you dead or alive? Is someone pregnant or not? Like, these are things that are off or on. Nominal means 3 or more categories where they're unordered. So the example I did last time, 1 equals dog, 2 equals cat, 3 equals rabbit, I think. I was going to go with guinea pig. But those aren't numbers. Those are kinds. But we would not reasonably agree on what is more. Like they're just separate things. Academic program is an example of a nominal variable. Ordinal is a tricky one. Ordinal is 3 or more choices that have some undeniable order, but the distances between the numbers don't necessarily mean anything. So a classic example of this is what some folks would call a Likert scale. It's actually pronounced Likert. Ask the Google. I came across a very funny subreddit once where a professor actually knew the guy and called him in the middle of class to ask him to pronounce his name. It's Likert, according to that person. So I don't use that word anymore because it actually refers to a scoring convention that the article showed did not work any better than just treating these as numbers. I would just call this an ordinal scale. So you've seen a million of these, I'm sure, in your lifetime, right? Check 1 if you strongly disagree, check 2 if you disagree, etc. How often do you do this? 0 is rarely, 1 is sometimes, 2 is often. Like, assuming that you pick labels that are sufficiently distinct, we could all agree about the order in which these go, right? Strongly agree is a more positive response than just agree, which is more positive than disagree. But these numbers are just labels. They don't mean anything. I could label these 1, 20, 300, and 4,000, and this is equally valid. So I make that point because a lot of folks want to treat these as numbers in analyses, and I would caution you not to do that, or at least to test whether that's a reasonable thing to do before doing so. And I will show you how to do that this semester. And by the way, the idea of categorical as a label has a million synonyms. So you might know this as a discrete variable, as a qualitative variable, as a grouping variable. In R, it's called a factor variable. It's called a class variable in SAS, and I don't think Stata has a name for it. Do you know? Does it have a special term? Categorical? Okay. So if you come across these synonyms, know that it is a variable that is kinds, not amounts. Okay. Good with that? All right. The other kind, big overarching category, is numbers, quantitative variables, or I say this is continuous sometimes. And this is where we're talking about at least interval measurement, where the numbers actually mean something. This is the kind of variable that we're going to learn to predict this semester in our models. One complication potentially is when they have 1 or more boundaries that control what their possible values are. So for instance, if you have the number correct on a test, that's a number, right? I got 1 right, 2 right, 3 right, 4 right. But it's not really a continuous variable because what's the worst that can happen? 0. What's the best that can happen? All of them. So depending on who is in your sample and what kind of test it is, you can end up with a pile of people who did really badly, that's called a floor effect, or a pile of people who did really well, that's called a ceiling effect. So we can think of this as a number, but we have to also be mindful of the fact that it's a number with a boundary. And if you were to predict these types of variables with a model, we want to make sure the model understands where those boundaries are. Otherwise, it's going to be like, I predict that you get -12 right. Like, oh, that's harsh. But that would not be a realistic prediction. Another type of variable that has a boundary is what's known as a count. So this would be the number out of an unknown possible. So how many cigarettes have we smoked today? Well, the lowest is 0. You can't smoke -1 cigarettes, I don't think. Maybe that's Nicorette? Would that count? At less than 0? Actually, no, that still has nicotine, so that's got to be another thing. But the maximum possible is I don't know. Count variables have special cases involving zeros. This is vocabulary you might see. If there's no zeros possible, that's called 0 truncated. And if there's more zeros than expected, then that's a 0 inflated count. So in the previous example, number of cigarettes smoked, what you are likely to see in a distribution, if you ask both smokers and non-smokers that question, you'll see a huge pile of zeros that is all the non-smokers plus the smokers who haven't gotten around to smoking yet. And then you have some kind of distribution after that. That's what's known as zero inflated. And these cases are all covered in the generalized class, by the way, because that is for not continuous outcomes. Other outcomes are continuous, but they may not be unbounded. So this semester, we're working with things that are supposed to be numeric, supposed to be continuous enough, ideally don't have boundaries, but in practice you may end up with them. So the key word is plausible. And so I have a word that I use to describe this where it's not truly continuous, but we're going to pretend it is, and I call that continue-ish. That's my word, not a real one. So here are some example continue-ish variables that you might predict with a general linear model. One is ordinal treated as interval, like that is a thing people say. So for instance, if I asked you one question with 4 choices, strongly agree, disagree, agree, strongly agree. I just said those aren't numbers, right? They're not. They're kinds. They're ordered kinds, but they're kinds. But what if I ask you 10 questions and they're all on a scale of 1 to 4? What do people do with that? What do you see happen on a survey instrument, for instance, or a test? Add them up, right? I'm going to quote Fall Out Boy. Add them up, add them up, up. Thanks to my son, I know who that is. Fire! Add them up. So somehow, even though we started out with things that aren't numbers, we're going to add them together and call them numbers. People are like, that's totes fine with me. Ugh. So something like this, we're saying it's continue-ish. There is still a boundary, right? If you answered 1 to every question, you get a 10. If you answer 4 to every question, you get a 40. But there's enough variation in the middle that we're comfortable thinking of that as a continuous variable. The same thing would happen if we had something like percent correct, right? Like it's continuous from 0 to 100 if it's percent, or 0 to 1 if it's a proportion, but there's still 2 boundaries. Others are interval, but also bounded on maybe one side, so something like response time. Any cognitive folks in here measure response time quickly? No? Just me? Okay, I'm the cognitive psychologist today. I used to live in a world of visual attention tasks where we'd measure in milliseconds how long it took people to look at something or answer a question. What's the fastest you can do something like that? 0, probably a lower bound of 200 milliseconds if you want to get into the nervous system, but 0 comfortably. Yeah, you can't have negative milliseconds of something. So response time is very much continuous, but it has a lower bound. Latent trait estimates. So if you analyze, say, GRE scores, or what's the TOEFL? There's another one, all the entrance exams, right? Those are latent trait estimates that they have given you that are supposed to be continuous, but they do have boundaries. What's the worst you can do on the GRE? Is it 120, 130, something like that? I don't know. When I took it, it was on a scale of 300 to 800. That's what the version I know. So these things are treated as continuous, but they're not exactly. They're probably good enough in practice, but one of the things that we'll pay attention to is whether the model predicts outside of bound values, and that would be a sign that it's not the right kind of model. So big picture, variables are either kinds or numbers. There's subdivisions within those kinds. But kinds versus numbers is going to dictate how we think about summarizing them univariately. One more is ratio. You're never going to see that. We don't have any ratio measures in the social sciences, but you can just treat that as a number. It's fine. So, in terms of summarizing this information, what would you need to report to describe this variable to an interested audience in your research or in your employment? Distinctions among categorical predictors will always matter. Distinctions among quantitative matter more when it's an outcome. So for categorical, it's really easy. All we would want to report is the frequency of occurrence of each possible category or the proportion. So how many people out of 100 answered this way, that way, this way? Usually we can make a picture to show this better and have it be displayed more readily, and adding value labels will really help your audience. So for instance, here's what it would look like in code and output. I have in example 1, a variable for marital status that has 5 possibilities. So married, widowed, divorced, separated, or never, haven't been married yet. First off, what kind of variable is this? Feel free to read from the screen. Nominal. Yes, I usually seed my responses somewhere on the screen. I'm shameless in encouraging audience participation. So this is nominal, right? Is like 5 never like more than separated or more? No, they're just different kinds. So it wouldn't make sense to try to aggregate these further down, like they're each their own thing. So here are the number of people in this sample that fall into each of these categories. If I remember correctly, yep, there's 734 people in this example. It's from the General Social Survey in a particular year. I got it from one of the Stata data sets. So in R, there is a command in base R called table. What it wants to know here, this is a function. X is what would you like the table of? And in R, the answer has 2 parts to it. The first part is the name of the data set, because in R you can have multiple data sets active at the same time. It has to know which one. So example 1. And then a $sign, because if you learn R, someone will pay you someday so that they don't have to, apparently. And then the name of the variable in question. So the name of my variable is called marital labeled, to differentiate it from the unlabeled version. After a comma, the next thing that I tell it is use NA. That stands for missing in R, not applicable or not answered, something like that. Equals if any. So like this makes no sense in English. You just have to understand what the people who made this intended. This means include a column for any missing. So if I had missing responses, that would show up as another category here, what you usually would want to do. You want to know how many people are missing. So these are raw frequencies. You can kind of eyeball them and get a sense as to which is relatively more common, but expressing these as proportions is probably easier for your audience. So I can do that in R by extending this table thing. So the interior right here is this part up here, and I put on the outside prop table, which changes it into a proportion. So then I get the proportion out of 1 that is each of these categories. So now I can look at it. Most of the sample is married. The next option is never, followed by divorced, followed by the others. In Stata, less words, tabulate. In Stata, you can only have one data set open at a time, at least within the version that I'm most used to seeing. The later versions of Stata have some way to do that, but I haven't bothered to learn. So it's just the variable marital. Comma, missing, means the options show missing values, and it spits out this table. So it has both the frequencies, as well as the percents, as well as the cumulative, which doesn't make any sense in this case. Now note the difference between percent and proportion. Okay? This is going to be one of your homework questions. So I'm going to ask you to run frequencies on a data set and tell me how many people are in each category, as well as what proportion is in each category. If you answer 45.91, that will be incorrect. It's looking for 0.4591 as a proportion. So percentage is out of 100, proportion is out of 1. So you could put a table like this, say, in a presentation, and people would know what it looks like, but tables of numbers in presentations are almost always a bad idea. Instead, you put in a picture. This is either a bar chart, a bar plot, or a histogram, depending on who you talk to. But this is expressing the percent of cases for each of these categories. So this is much easier for your reader to be like, yeah, most of my sample is married. To make this picture, this is Stata. The command is called histogram. It wants to know what variable you want to make it for, and the rest of these are options. Treat it as discrete, do it in percent, and this refers to the x-axis and that it wants me to put the labels on there. So the 1.married, 2.widowed, that convention, those are labels. The way that this variable is stored is just 1, 2, 3, 4, 5. But if I make a plot that says 1, 2, 3, 4, 5 at the bottom, no one's going to know what that means. So labels are imperative. In R, here's a bar plot, as it is called, with the same information, where it's a little bit more convoluted to tell it what to do. Like, what do you want me to do with the height? Well, I'd like you to make a height out of the table that is this variable. So you're like stacking these things together. And note all the parentheses in here. Like this is the part that I say is really easy to screw up at first because you have to make sure that everything is closed, that you finished. In RStudio, it will yell at you if you're off. Like there will be a little angry red X on the line you're off, and so you have to be like, which closed parenthesis did I not get? This is where having examples of how doing what you want to do is going to make a difference. So let's say that I gave this to you in your homework and I said, make me a bar plot for favorite kind of pet. What would I need to change? Well, I need to find what's the name of my data, what is the name of the column for favorite kind of pet, and then I need to change the label that goes with it. And that's it. So you can borrow the structure and modify it to do what you need to do. To trick it into doing percentages, that's how this picture was made. I wrapped the interior into prop table instead, the same way. There is all kinds of fancy stuff in R to make pretty pictures. I have not bothered to learn most of that. But ggplot and ggplot2 are the ones that I see people use most commonly. Any others? No? Yep. And honestly, I end up making pictures in Excel a great deal of the time for a couple different reasons, but one of which is because if my collaborators don't use R or Stata, and I'd have to remake the picture every time they decide they want to use the labels a little bit differently, it's a lot easier for me to give them an Excel file and be like, here you go, you figure out what you want. I don't have to rerun it each time. So what about quantitative variables? Here is a table showing the frequency of each possible response to a variable in this data set that is called income and is in thousands. Now clearly this is not continuous because there are these specific choices and multiple people pick them. So these were clearly ranges of income that you had to endorse. But if you look at these values, just looking at the relative frequency of this doesn't give me a sense as to how rich my sample is. Like this is not helpful for a quantitative variable. Neither is the same kind of bar chart. Like knowing how frequent each specific value was is weird because it doesn't pay attention to the relative distances between these numbers. This is just each specific answer. So for data that are quantitative, I can make a similar kind of picture to display it, but I don't want each separate individual value. What I want is something called a histogram, where we sort of round things into convenient bins. So say all data points from 0 to 500 in here, 500 to 1,000 in here, 1,000 to 1,500 in here. And the software does this for you, by the way. This isn't something you need to do manually. So the code for that is very similar. Histogram still in Stata, leaving out the discrete option. I tell it how wide the bins are, so in units of 5, starting at 0. In R, the command is hist. I can do it for income. I want the frequencies, and I want 15 bins, and here are the labels. And so here are the pictures that I get. So it matters less, I think, how many bins you make and how wide they are. And that depends on the distribution of your variable, what its possible values are. But this kind of picture says very quickly, is this sample relatively rich or relatively poor? Relatively poor. As I said here, there's a lot fewer people who make more money than who make less money. So this shows you very quickly like what you can expect. Like obviously there is a boundary here because you can't make negative money. I think that's when you're overdrawn on your bank account actually. Then you can make negative money, but not in this sample. And money theoretically goes up to infinity, just ask the billionaires, but in this sample it's capped at 80 is the highest one here. So for numeric information, we still would like to make pictures, but they're of a different kind. Now, how do we summarize this? I just said that I don't think it's useful to say how many people were in each particular category, and you may have way too many categories to do that. So what we would do instead is think about summarizing that distribution. So you will hear me say that word a lot. I'm referring to basically the overall shape of this thing. And I have 3 different ways that I want to summarize it. Where the middle is, essentially how wide it is, and how lopsided it is. You know where I'm going with this. This is my version of it. The statistician in me, buried very deeply, would say, number one, where the middle is central tendency. And when I first started teaching this, I was like, who knows what a mean is? And I had a student say, the same thing it was in 6th grade? Yes. I wasn't mad about that because she wasn't wrong. Like, yeah, you know what a mean is. You know how to compute a mean. That's not a big deal. But there's also median and mode. So mean is the arithmetic average, and there are more than one kind. There's geometric means and harmonic means and other kinds. Median is the middleist. And those are not the same number. I've had to correct other faculty members on this point before in my life. Because we were talking about teaching evaluations in one context, and whether we should give bonus points in our evaluation to teachers who have higher than the average. And one said, well, by definition, don't half of them have to be higher than the average? Tell me why that sentence is wrong. What is, by definition, half? That's median, right? Or 50th percentile is the other way people talk about that. So these are 3 different ways, mean, median, mode, of characterizing middle. They will not necessarily converge to the same answer. Spread, dispersion, you can think of in 2 related ways and one that's a little different. Standard deviation. Is this a term we've heard before? Some folks, like I guarantee you've heard it at some point. It may not have been in this context. It will be abbreviated SD in a lot of my slides and in your results. This is how far off on average any one person is from the mean. If I square that number, that gives me variance. So this you will see across the semester, these 2 versions, because sometimes we talk about it one way and sometimes we talk about it the other way. The reason we square things is to keep the negatives and positives from canceling out. That's the easiest way to put it, because you can be off this way or you can be off that way. So if you want to talk about average offness, that's standard deviation. If you want to talk about sort of the collection of offnesses, that's variance. If you want to do it differently, another way that people talk about spread is something called interquartile range, which is the distance between the 75th and 25th percentiles. So that's more in data that are not necessarily symmetric. And the last one is how lopsided it is, asymmetry or skewness. And this is caused by natural boundaries. So like number of cigarettes smoked is going to have skewness because you can't go past 0. If you have a ceiling effect, like you give a test and everyone does well and they can't go past perfect, that will cause skewness. It's something that you pay attention to, but isn't necessarily something that you need to solve or otherwise address. So as a pictorial example, here is a histogram. These pictures came from SAS, by the way, where I simulated data that have a mean of 100 in both, and the standard deviation on the left is 10. 10 squared is 100, that gives me variance. The standard deviation on the right is 15, squared gives me variance of 225. So the middle is still the same. It's how wide around it is. Now this matters in terms of thinking about prediction. The more spread out people are, the less certain you can be that the mean is going to accurately describe any of them. And the mean may not be accurate at all. So for instance, I have a son who is 9. His big sister is almost 18. So on average, how old are my kids? They're somewhere in the middle, like 12, maybe 13. I can't do the math in my head. I told you we don't do computations in this class. 13-ish, right? But can I think of either of them as a 13-year-old? No, like one is driving and sending off her college applications and the other, like, wants me to read to him at night. So like 13 is not an accurate representation of my household because of the variance around it. Both matter. So standard deviation is how far off any one person is from the mean on average. Squaring that gives you variance, the collection of offnesses. Here is a picture showing divergence of the 3 measures of central tendency due to skewness. So if I have what is known as positive skew, it is named for which way it falls off, or the tail goes. This is counterintuitive. So the left one is positive skew because the positive side of this is where the tail is heading to. The middle is symmetric or symmetrical I always say symmetric, but whichever. This person decided it was symmetrical. And then negative goes this way. So if you have like count data, for instance, where it's bounded at 0, you're almost guaranteed to have a positive skew like this. If you have a ceiling effect, you're almost guaranteed to have negative skew. So the mean gets pulled towards the skewness. If there is no skewness, then the 3 measures are going to stack on top of each other, but if not, they'll diverge. So an example that you might be familiar with from real life, when people talk about houses, they never talk about the mean home price. It's always the median home price. Because homes are positively skewed, right? What's the most expensive a house can be? Like infinity. I think I saw something on the news about like the most expensive house ever was like 175 million or something in our country. I don't know. But I know that that's not like modal experience for people. So if we computed a mean house price, the super rich people would drag that way away from the rest of us. And that's not a good description of where the middle is. So median is actually going to be less because it is going to be less biased by the extreme cases at the end. And the opposite happens here. If we have people that are dragging the mean extra low, median is going to be higher as a consequence, and then mode as well. So if you're concerned about skewness or asymmetry, that's where you would want to make sure you report means and medians as opposed to just means, which are the defaults, as it tends to be. Okay. I don't know if I want to go there. Well, even I'm like, oh my God, look at all these words. Again, not apologizing. I dump everything in the slides so that you can listen instead of write. And actually, during the pandemic, I had people on walking on treadmills during this class. And I was actually really proud of that. Like they were multitasking, getting their stuff done, because it was just about thinking and not writing everything down. But what I was going to say about this is when I took IntroStat and when many of you had, a big deal was made about population this and sample this, and population had this notation and sample had that notation. That's going to fall apart real quick. I have a little bit of that on the slides that follow here, but it's always kind of this hodgepodge in practice of Greek letters and regular Roman alphabet letters. And I think that's because when people start doing models on data, it's assumed that we don't know what the population is. We can't know what the population is unless you make up the data. What we have is a sample. And so we talk about trying to make inferences to a population, but we know that we only have the one sample. So I present a little bit of this just so that you've seen it and connect to it from what you've had before, but not gonna pay a whole lot of mind to it. It'll be a hodgepodge. But that's what follows, is how to calculate all of these things. And by calculate, I mean make the computer do it for you. Okay? All right, 313. I think that is a good spot to say questions before we call it a week. Yes?
Is it possible to, like the negative skew, to have the mean less than the median?
I don't think it is. I don't think it is, but I would have to look that up to be absolutely certain.
I haven't encountered, but...
Yeah, like the logic is that the mean is being driven
Right.
like differentially by
Right.
these extreme cases, and there's a lot like, you know, they're pulling it, essentially, is the way I think about it. It's being pulled towards them, and so the middle is not where it should be.
But we have enough pull.
Yeah, so just to put a placeholder in this, all of the models that we're doing are going to predict the mean. But it's going to be a conditional mean based on the other information, like the mean for this group, the mean for that group, that kind of thing. But if you're in the situation where you kind of don't believe the mean and you want to predict the median instead, that is called quantile regression, and I teach that in the generalized course. That is a thing. And you can not only predict the median, you could predict the 25th percentile, the 33rd percentile, anything you want in that method. Yeah. All right, other questions? All right, then we made it through our first week. Huzzah! You all have a 3-day weekend. So no office hours or anything on Monday. I will see you Tuesday. Thanks for being here. Let me know if you need anything. Work on homework 0. Bye, Zoomers.